This next lesson, you might want to think hard about some of the information that's in here. A normal line, by the way, if you haven't been thinking, then you should change.
I've been doing a lot of thinking.
Well, I'm glad you've been doing a lot of thinking. That's great. So a normal line to a surface at a point, p, x, y, z, 0, this point or this point or this point, would be a place where when struck at p by a ball traveling along the normal line, the ball would bounce directly back the path it came in on if there was no such thing as gravity pulling it down. So in other words, a ball comes in, bounces here, would bounce straight back. It's a normal line. Bounces here, bounce straight back. Bounces here, would bounce straight back. And there are three normal lines drawn in purple on the graph here. Well, I just showed you those three and showed you the points I was talking about. So I hope you understand that one here would be bouncing back this way, maybe. So note that we can find a normal line at a point on a surface. If we can, then we can also find the plane that the line is normal to. In other words, the tangent plane to the surface at that point. In other words, we've got a normal line here, but there's also a plane that's orthogonal to that normal line, or every line in that plane is orthogonal to that normal line, whatever we would want to call that. So let S be a surface given by f of x, y, z equals 0, and you know, if we have a function of two variables, you can make it that. And let p of x0, y0, z0 be a point on the surface S. And let C be a curve on the surface S that goes through P with the curve defined by a vector valued function r of t equals x of ti plus y of tj plus z of tk. So in other words, here's what we got. We got a surface, and we've got a curve on that surface defined by a vector valued function. So since the curve is on the surface, then f of x, y, t, x, y, z, actually, so f of x of t, y of t, z of t equals 0. Since it's on the surface, and that's the equation of the surface. So since C is on the surface, then f of the xt, yt, and z of t equals 0. Now, suppose f is differentiable and x of t, x prime of t, y prime of t, and z prime of t all exist. Then from the chain rule, the derivative of f at t would be the partial of x of x, y, z times x prime of t plus the partial of y of x, y, z times y prime of t plus the partial of z of x, y, z times z prime of t, and that would be equal to 0 since the derivative of a 0 equals 0. So the derivative of this function is 0. After all, this function is 0. So that's equivalent to saying that 0 equals, now this is the cool part, del f of x 0, y 0, 0, z 0 dotted with r prime of t. See, del f would be x prime of t I plus y prime of tj plus z prime of tk, right? And so, look, that's what this is. When you dot this with r prime of t, that gives us this lovely expression right here, and it equals 0. So that means the gradient at p is orthogonal to the tangent vector of every curve on S that goes through P. All of these tangent lines at P lie in a plane normal to the gradient that contains P. So, here's the definition of the tangent plane and the normal line. Let f be differentiable at the point P, x0, y0, 0, 0, z0, on the surface S given by f of x, y, z equals 0, and you know if you have a surface as a function of two variables, you can convert it to that, such that the gradient at P is not the 0 vector. That would take all the fun out of it if it was. Then the plane through P at that the plane through P that is normal to the gradient vector at P is called the tangent plane to S at P. And the line through P having the direction of the gradient at P is called the normal line to the surface at P. So to find the equation of the tangent plane to S at P, to the surface at the point P, let x, y, z be an arbitrary point in the tangent plane, and then the vector v equals x minus x0i plus y minus y0j plus z minus z0k lies in the tangent plane. Since the gradient is normal to this vector, in the tangent plane we have del f of x0, y0, 0 dotted with v of t equals 0. So here's the equation of the tangent plane. It's theorem 13.13. If f is differentiable at a point, then the equation of the tangent plane to the surface at that point is given by partial derivative of f with respect to x times x minus x0 plus partial derivative with respect to y times y minus y0 plus a partial derivative with respect to z times z minus z sub 0, and that all equals 0. So let's do an example. Find the equation of the tangent plane at 0, 2, 0 to the paraboloid and sketch it. Well, I sketched it above, so we've seen the picture of it. So if this is our paraboloid, z equals 4 minus x squared minus y squared, and f of x, y, z is 4 minus x squared minus y squared minus z, and that means our partial with respect to x, negative 2x. Our partial with respect to y, negative 2y. And our partial with respect to z, negative 1. So del f is negative 2xi minus 2yj minus 1 times k. And the tangent plane is, at this point where x is 0, y is 2, and z is 0, well, x is 0, so negative 2 times 0 is 0, so 0 times x minus 0. Y is 2, so we got negative 4 times y minus 2. And we also have, well, it doesn't matter, since the k coefficient is just negative 1 no matter what x, y, and z are, we've got negative 1 times z minus 0, and that equals 0. And if you simplify all this, you get the plane 4y plus z equals 8. And I'm going to graph the surface and the tangent plane. The tangent plane is 8 minus 4y, and the surface is the paraboloid we saw earlier. And hopefully you'll be able to see the graph of the surface, and the surface is that paraboloid that we looked at before, and at the point x is 0, that's x is 0, y is 2, so right about here we can see, you can kind of see that the plane is, or the surface is tangent there, because you can actually see a little blob of surface paint if you want to call it that at that point. But there is that tangent plane at that given point. And so that's pretty phenomenal that I can show you this with my software, and if I tried to draw that on the blackboard, I might spend a couple days on that before I made something like that believable and visible. But now I can see it from lots of angles, and isn't software wonderful, and isn't it nice to be able to teach a class like this through the web?
I've been doing a lot of thinking.
Well, I'm glad that you have.